The universe is full of mysteries, from enormous walls of galaxies stretching across billions of light years to mysterious glowing blobs in the depths of space. These cosmic phenomena challenge what we understand about the universe, each of these structures telling a story, not just about the vastness of space, but about the forces that have shaped everything from the beginning of time. They remind us that even in an era of advanced technology and scientific discovery, the cosmos is still a place of wonder and the unknown. Let's delve into what makes these structures unique, the science behind them, and the mysteries that remain unsolved. The Hercules Corona Borealis Great Wall, the largest structure in the universe. The Hercules Corona Borealis Great Wall is a structure so vast it defies comprehension. Its name hints at its location, stretching across the constellations, Hercules, Corona Borealis, and a few neighboring regions. For many, this discovery challenged long-standing ideas about the universe's organization and raised questions about how such a colossal formation could exist. Astronomers first identified the Hercules Corona Borealis Great Wall in 2013. They were studying gamma-ray bursts, brief but intense flashes of gamma radiation thought to be the death throes of massive stars collapsing into black holes. These bursts occur billions of light years away, and their distribution provides clues about the structure of the universe on the largest scales. When researchers mapped these bursts, they noticed something extraordinary: an unexpected concentration of gamma-ray bursts clustered together, suggesting a massive structure unlike anything previously known. The universe is not randomly scattered with galaxies and matter. Instead, it forms a vast network of filaments, walls, and voids, with galaxies arranged along these structures like beads on a string. This web-like structure is the result of billions of years of gravitational interactions since the Big Bang. However, the universe also obeys what is known as the cosmological principle. This principle states that, on large scales, the universe should be homogeneous and isotropic, essentially the same everywhere, without any preferred direction or location. The Hercules Corona Borealis Great Wall seems to defy this principle. Measuring an estimated 10 billion light-years across, it dwarfs other known cosmic structures. For comparison, the Sloan Great Wall, another enormous structure, spans only about 1.4 billion light-years. The sheer size of the Hercules Corona Borealis Great Wall makes it difficult to reconcile with our current understanding of how matter should be distributed in the universe. If the cosmological principle holds, structures of this size simply shouldn't exist. Scientists have spent years studying this structure to determine whether it is a real physical entity or an artifact of the data. The evidence so far suggests that it is real. The gamma-ray bursts linked to the Hercules Corona Borealis Great Wall are not random. Instead, they appear concentrated in a way that aligns with the presence of a massive structure. The scale of this alignment points to a coherent and organized formation of galaxies, clusters, and superclusters bound together by gravity. One of the most puzzling aspects of this discovery is how such a massive structure could have formed in the 13.8 billion years since the Big Bang. The growth of cosmic structures is governed by the interplay between gravity and dark energy. Gravity pulls matter together, forming clusters and filaments, while dark energy drives the expansion of the universe, counteracting the effects of gravity. For the Hercules Corona Borealis Great Wall to exist, gravity would have needed to overcome dark energy on a truly staggering scale. This raises questions about whether our understanding of dark energy, gravity, or the early universe might be incomplete. If the universe is not as uniform as previously thought, it could mean revising key assumptions about the cosmos. Some scientists have even speculated that such structures might hint at unknown forces or phenomena influencing the distribution of matter on the largest scales. Standing on Earth, it's easy to feel small in the face of vast distances and massive celestial objects. But the discovery of something as enormous as this structure stretches our sense of scale to its limits. It reminds us that, despite centuries of exploration, we are still only beginning to understand the cosmos. The local void, a mysterious cosmic desert. The local void is a vast, nearly empty region of space, stretching about 150 million light-years across, where galaxies and matter are notably sparse. Compared to the rich clusters and filamentary structures that dominate much of the observable universe, the local void stands out as a place of profound emptiness. The local void lies adjacent to the local group, the collection of galaxies that includes the Milky Way and its closest neighbors, such as Andromeda and the Magellanic Clouds. Despite its proximity, the local void has been challenging to study because it contains so little luminous matter. Galaxies, stars, and other bright objects are the tools astronomers use to map the universe. And in the absence of these, the void appears as a blank space in the cosmic landscape. Galaxies do not move randomly through space. Their motions are shaped by the gravitational pull of surrounding matter. In regions of high density, such as galaxy clusters, gravity pulls galaxies inward, creating tight, dynamic systems. In contrast, voids like the local void exert an opposite effect. With so little matter inside, voids lack the gravitational pull to attract galaxies. Instead, galaxies near the edge of a void are effectively pushed away, moving toward regions of higher density. This pushing effect is not caused by the void itself, but rather by the gravitational pull of matter outside the void. Imagine the universe as a landscape of hills and valleys, where matter gathers in the hills and leaves the valleys empty. Galaxies naturally roll downhill toward the hills of matter, away from the valleys of emptiness. The local void is one of these valleys, and its emptiness creates a kind of gravitational imbalance that shapes the motion of nearby galaxies. Our galaxy is moving through space at hundreds of kilometers per second, and while much of this motion is driven by the pull of nearby structures like the Virgo cluster and the Great Attractor, the local void plays a subtle but significant role. Its lack of matter creates less resistance and contributes to the overall direction and speed of our galaxy's movement. The question of why the local void is so empty remains unanswered. In the early universe, matter was distributed unevenly, with regions of higher density eventually forming galaxies, stars, and clusters, while lower density regions became voids. Over time, gravity amplified these differences, pulling matter into dense regions and leaving voids even emptier. However, the sheer size and emptiness of the local void suggest that it may have started with an exceptionally low density of matter, even compared to other voids. Another possibility is that processes within the void have actively prevented the formation of galaxies and stars. For example, the conditions within the void may not have allowed gas to cool and condense into the dense clouds needed for star formation. Without stars and galaxies to illuminate the void, it has remained a dark and barren region, largely invisible to our telescopes. Despite its emptiness, the local void is not entirely devoid of matter. Like other voids, it likely contains dark matter. Dark matter does not emit or absorb light, but its gravitational effects can be observed. Within the local void, dark matter may form a faint, diffuse network, too spread out to create galaxies, but still influencing the motion of matter at its edges. The study of the local void has been made possible by advancements in galaxy surveys and mapping techniques. By observing the distribution of galaxies in 3 dimensions, astronomers can identify the boundaries of voids and measure their size and shape. In the case of the local void, these surveys have revealed its vast extent and its influence on the surrounding cosmic structures. Voids are among the largest structures in the universe, yet they are defined by their emptiness. This paradox makes them valuable for testing theories about the universe's evolution and composition. For example, voids are sensitive to the effects of dark energy. By studying the shape and growth of voids like the local void, scientists can gain insights into the properties of dark energy and its role in shaping the cosmos. The Large Quasar Group, a controversial gigantic arrangement. Discovered in 2012, the Large Quasar Group, or LQC, is an arrangement of quasars that spans an astonishing 4 billion light-years, making it one of the largest known structures in the observable universe. What makes the LQG particularly controversial is whether it should even be considered a true structure at all. Quasars are some of the brightest objects in the universe, powered by supermassive black holes actively consuming matter. As this material falls toward the black hole, it heats up and emits enormous amounts of light and energy. Quasars are often found at the centers of galaxies, and their intense brightness allows astronomers to detect them even from billions of light-years away. This makes quasars valuable tools for mapping the universe on its largest scales. The Large Quasar Group was identified when astronomers studying the distribution of quasars noticed an unusual clustering in one part of the sky. Instead of being scattered randomly, as one might expect, these quasars appeared to form a loose but coherent arrangement stretching across a vast region of space. This apparent grouping led to the designation of the LQG as a large-scale structure. The boundaries of the LQG are not as clearly defined as those of walls or filaments, and its members, individual quasars, are separated by immense distances. Unlike galaxy clusters, which are held together by gravity, the quasars in the LQG are not necessarily bound to one another. This has led some researchers to argue that the LQG is more of a statistical artifact than a genuine physical entity. Supporters of the LQG's classification as a structure point to the statistical significance of its alignment. The likelihood of so many quasars appearing in such close proximity by chance is considered low, which implies that there may be an underlying connection between them. Some have proposed that the LQG could be part of a larger filament of the cosmic web, with quasars tracing the distribution of matter along this filament. If true, this would provide a link between the LQG and other large-scale structures, reinforcing the idea that it is a genuine feature of the universe. On the other hand, critics argue that the apparent grouping of quasars could be the result of observational biases or limitations in the data. Quasars are distributed unevenly across the sky, and their brightness can vary depending on factors such as distance and orientation. These variations might create the illusion of a structure where none exists. Additionally, the methods used to define the boundaries of the LQG are not universally agreed upon, further complicating its classification. This debate highlights the challenges of studying large-scale structures in the universe. Unlike smaller objects like stars or galaxies, which can be directly observed and measured, structures like the LQG are inferred from patterns in the distribution of objects. This makes their classification more subjective and open to interpretation. As more data becomes available from new surveys and telescopes, astronomers hope to refine their understanding of the LQG and determine whether it represents a genuine feature of the cosmic web. Regardless of its classification, the LQG provides valuable insights into the nature of quasars and their role in the universe. Quasars are not distributed randomly. Their positions are influenced by the underlying distribution of matter. This means that studying quasars can reveal the large-scale structure of the universe, even in regions where galaxies are too faint to detect. Quasars are thought to be powered by supermassive black holes, which form in the centers of galaxies. For a grouping of quasars like the LQG to exist, there must have been regions of the early universe where galaxies and black holes formed in close proximity. This suggests that the LQG may trace a particularly dense region of the cosmic web, where matter was concentrated enough to give rise to multiple quasars within a relatively small volume of space. Quasars are often associated with periods of intense star formation and galaxy mergers, events that can fuel the growth of black holes. By examining the properties of the quasars in the LQG, astronomers can learn more about the environments in which these objects form and evolve. This, in turn, can provide clues about the role of quasars in shaping the universe's structure and history. The Sloan Great Wall, a 1.4 billion light-year mystery. Though not as large as the Hercules Corona Borealis Great Wall, the Sloan Great Wall is another colossal structure in the universe, with its size and complexity making it one of the most fascinating discoveries in astronomy. Stretching across 1.4 billion light-years, it is a dense region of galaxies, galaxy clusters, and dark matter that form a wall-like shape. Its discovery in 2003 through the Sloan Digital Sky Survey, or SDSS, marked a turning point in our understanding of the universe's large-scale structure. The SDSS was designed to create detailed maps of the sky. It uses powerful telescopes and advanced imaging systems to capture light from millions of galaxies. By measuring the distances to these galaxies, astronomers can build three-dimensional maps of their positions in space. When researchers analyzed this data, they noticed an enormous coherent structure that became known as the Sloan Great Wall. Like the Hercules Corona Borealis Great Wall, the Sloan Great Wall appears to challenge the cosmological principle. If the universe is supposed to look the same on large scales, then why do we see something so vast and irregular? Scientists began investigating whether this structure could fit within the standard model of cosmology, which explains how the universe evolved after the Big Bang. The standard model predicts that galaxies should form along filaments in the cosmic web, but there are supposed to be limits to how large these structures can grow. Gravity works slowly, pulling matter together over billions of years, while the universe's expansion pushes matter apart. For a structure like this to form, the regions of space that gave rise to it would have needed a significant amount of matter and time to coalesce into its current state. Some researchers have suggested that the density of matter in this part of the universe may have been higher than average in the early stages of cosmic evolution, allowing gravity to work more effectively in pulling material together. The Sloan Great Wall is not a solid object. Instead, it is made up of galaxies and galaxy clusters separated by large voids. These voids are vast regions of space that contain very few galaxies, giving the wall its distinct web-like appearance. The galaxies themselves are bound together by dark matter, an invisible form of matter that does not emit light but exerts gravitational force. Dark matter acts as a kind of scaffolding, holding the galaxies in place and shaping the overall structure. One of the most striking features of the Sloan Great Wall is how it reveals the way galaxies cluster. Galaxies are not randomly distributed in space. They tend to form groups, clusters, and superclusters. These clusters then connect to form larger structures like the Sloan Great Wall. Studying these patterns helps scientists understand the forces that govern the universe. For example, the clustering of galaxies can provide clues about the nature of dark matter and dark energy. Other structures of similar or larger scale, like the CFA2 Great Wall and the Hercules Corona Borealis Great Wall, have also been discovered. Each of these structures contributes to a growing picture of the universe as a vast, interconnected web. However, the Sloan Great Wall remains one of the best studied examples, thanks to the detailed data provided by the SDSS. Its discovery has sparked debates about whether our current models of the universe are complete. Some scientists argue that the existence of such large structures suggests that we may need to revise our understanding of cosmic evolution. Others believe that the Sloan Great Wall fits within the expected variations of the standard model, albeit as an extreme example. Studying structures like the Sloan Great Wall also sheds light on the processes that shape galaxies themselves. For instance, galaxies within dense regions like the Wall are more likely to interact with one another, leading to mergers and other events that can alter their appearance and behavior. These interactions play a key role in the life cycles of galaxies, influencing their star formation rates, shapes, and overall evolution. The Sloan Great Wall's discovery has inspired new questions about the limits of cosmic structures. How large can these formations become? Are there even bigger walls or filaments waiting to be discovered? As telescopes and surveys become more advanced, astronomers hope to map the universe in even greater detail, potentially uncovering new phenomena that challenge our understanding of the cosmos. The giant arc, a challenge to the cosmological principle. The giant arc is a massive structure composed of galaxies, galaxy clusters, and possibly dark matter, stretching across 3.3 billion light-years of space. Its name reflects its shape, a vast curved line of galaxies that arcs through the cosmos. The giant arc was discovered in 2021 by a team of astronomers studying the distribution of quasars. Quasars are extremely bright objects powered by supermassive black holes at the centers of distant galaxies. Because they are so luminous, they can be observed even from billions of light-years away, making them valuable tools for mapping the large-scale structure of the universe. As the researchers analyzed the positions of these quasars, they noticed an unusual concentration of them forming a curved shape. This pattern led to the identification of the giant arc. The discovery of the giant arc came as a surprise. While astronomers had already identified other large structures, such as the Sloan Great Wall and the Hercules Corona Borealis Great Wall, the giant arc stood out because of its unusual alignment. It does not appear to be randomly distributed within the cosmic web, but instead follows a coherent arc-like structure that spans a significant portion of the sky. This level of organization on such a large scale is difficult to explain using current cosmological models. If the universe is supposed to be isotropic and homogeneous on large scales, then structures like the giant arc should be extremely rare or non-existent. Yet, here it is, defying expectations and prompting scientists to reconsider what might be possible within the framework of the universe's evolution. Some scientists speculate that it may have formed in regions of the early universe where matter was distributed unevenly, allowing gravity to pull galaxies into this unusual shape over billions of years. Others wonder if unknown forces or phenomena could be at play, influencing the distribution of matter on scales far larger than we can currently explain. When astronomers map the universe, they see not just isolated walls or filaments, but a network of interconnected features. The giant arc seems to align with other known structures in a way that suggests an underlying pattern. This apparent coherence across vast distances is difficult to reconcile with the idea of a random, isotropic universe. Studying the giant arc also provides insights into galaxy formation and evolution. The galaxies within the arc are not evenly distributed. They cluster together in some regions while leaving gaps in others. This uneven distribution offers clues about the forces shaping galaxies and their environments. For example, regions of higher density within the arc may have experienced more intense gravitational interactions, leading to the formation of larger galaxies or galaxy clusters. These processes help scientists understand how structures in the universe grow and evolve over time. Some researchers argue that its existence could be a statistical fluke, an unusual but not impossible alignment of galaxies that does not require revising the cosmological principle. Others believe that it is a genuine challenge to current models and that further study is needed to determine its significance. As more data becomes available from surveys and telescopes, astronomers hope to better understand the nature of the giant arc and its place in the cosmic web. El Gordo, the fat one of galaxy clusters. El Gordo, which translates to the fat one in Spanish, is one of the most massive galaxy clusters ever discovered. Located approximately 7 billion light-years from Earth, this colossal structure represents a snapshot of the universe during its earlier stages, offering a window into how massive galaxy clusters form and evolve. With a mass equivalent to about 3 quadrillion times that of the Sun, El Gordo has earned its nickname for its immense size and gravitational influence. Galaxy clusters like El Gordo are the largest gravitationally bound structures in the universe, consisting of hundreds or even thousands of galaxies embedded in vast clouds of hot gas and dark matter. What makes El Gordo fascinating is its extreme mass and unusual properties. Observations suggest that it is the result of a high-speed collision between two smaller galaxy clusters, a rare and energetic event that has left a lasting imprint on its structure and behavior. The hot gas within El Gordo emits X-rays due to its high temperature, reaching tens of millions of degrees. Observations from telescopes like NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton have provided detailed maps of the cluster's gas distribution. These maps reveal the turbulent effects of the collision, with shock waves and displaced gas creating a chaotic and uneven structure. Such features are consistent with the idea that El Gordo is still in the process of merging, a process that can take billions of years to complete. In galaxy clusters, dark matter acts as a gravitational scaffold, holding the cluster together and influencing the motion of galaxies within it. The collision that formed El Gordo has provided a unique opportunity to observe the separation of dark matter and normal matter. As the two clusters collided, their galaxies and dark matter passed through each other relatively unaffected, while the hot gas, which constitutes the majority of the visible mass, was slowed down and displaced. This separation creates a phenomenon known as a bullet cluster, where the dark matter's gravitational influence can be mapped using gravitational lensing techniques. Gravitational lensing occurs when the massive gravitational field of a cluster like El Gordo bends and distorts the light from background galaxies. By analyzing these distortions, astronomers can create detailed maps of the cluster's dark matter distribution. In the case of El Gordo, these maps have confirmed that dark matter dominates the cluster's mass and plays a crucial role in its overall structure. In the standard model of cosmology, galaxy clusters grow over time through the merging of smaller structures. The discovery of such a massive cluster at a relatively early stage in the universe's history suggests that the process of cluster formation can occur more quickly and efficiently than previously thought. The two smaller clusters that merged to form El Gordo were moving toward each other at an exceptionally high speed, estimated to be several thousand kilometers per second. This velocity is difficult to explain within the framework of standard cosmological models, which predict slower merger speeds for clusters of this size. Like other galaxy clusters, El Gordo contains a mix of galaxy types, from young star-forming spirals to older quiescent ellipticals. The collision and merger process has likely influenced the evolution of these galaxies, triggering bursts of star formation in some and quenching it in others. Studying these galaxies in detail can provide insights into how galaxy interactions and environments affect their development over time. It was first identified in 2011 through the Atacama Cosmology Telescope in Chile, which detected the Sunyaev-Zeldovic effect, a distortion in the cosmic microwave background caused by the hot gas in galaxy clusters. Follow-up observations using X-ray telescopes, optical imaging, and spectroscopic surveys confirmed its massive size and unusual properties. These multi-wavelength studies have provided a comprehensive view of El Gordo and its components, highlighting the importance of combining different types of data to understand complex cosmic phenomena. Hani's Vorp, a ghostly galactic glow. Hani's Vorp, which translates to Hani's object in Dutch, is a glowing greenish cloud of gas discovered in 2017 by Hani van Arkel, a Dutch schoolteacher, while participating in the Galaxy Zoo project. This citizen science initiative invited volunteers to help classify galaxies in images captured by telescopes, and it was through this project that Van Arkel stumbled upon a sight unlike anything astronomers had seen before. The Vorp is located near a galaxy called IC 2497, which lies about 650 million light-years from Earth. It appears as a large, irregularly shaped region glowing brightly in visible light with an eerie green hue caused by ionized oxygen. The light emitted by this cloud is not from stars or any luminous object within it. It is believed to be the lingering echo of a quasar. When a black hole is actively consuming matter, it generates an enormous amount of energy, often outshining the entire galaxy around it. The intense radiation from the quasar can ionize gas far beyond the galaxy, causing it to glow. In the case of Hani's Vorp, the quasar that illuminated the gas cloud appears to have turned off or gone dormant, leaving behind a glowing relic of its former activity. What makes Hani's Vorp particularly fascinating is its size and brightness. The cloud spans about 100,000 light-years, roughly the size of the Milky Way, and its glow is strong enough to be visible across vast cosmic distances. The fact that the quasar is no longer active adds to its mystique. When a quasar is active, it emits intense radiation and powerful jets of energy that can influence the evolution of the host galaxy and nearby objects. This process, known as feedback, can heat gas and prevent it from collapsing to form new stars, effectively halting star formation in the galaxy. At the same time, the energy from the quasar can ionize gas far beyond the galaxy, creating glowing regions like Hani's Vorp. Observations have shown that IC 2497 contains a supermassive black hole at its center, which likely powered the quasar that illuminated the Vorp. However, the quasar is no longer visible, suggesting that the black hole has stopped accreting matter, or that its activity has diminished significantly. The glowing gas in Hani's Vorp is thought to be a delayed reaction to the quasar's past activity, as light and radiation take time to travel across such vast distances. Astronomers have used a variety of telescopes to study Hani's Vorp in detail, including the Hubble Space Telescope and radio observatories. These observations have revealed the complex structure of the cloud, including regions of denser gas and areas where the glow is particularly intense. They have also detected signs of star formation within the Vorp, likely triggered by the interaction between the gas and the radiation from the quasar. This discovery highlights the dual role of quasars, which can both suppress and stimulate star formation depending on the circumstances. Quasars are thought to be episodic, with periods of intense activity followed by quieter phases. The sudden switching off of the quasar in IC 2497 suggests that these transitions can happen relatively quickly, at least on cosmic timescales. Understanding these changes is crucial for understanding the life cycles of galaxies and the role of supermassive black holes in shaping the universe. The discovery has inspired search for similar objects, leading to the identification of a class of phenomena known as Vorpjes, or little Vorps. These are smaller, fainter regions of ionized gas associated with galaxies that have undergone similar quasar activity. Studying these objects has expanded our knowledge of how quasars interact with their environments and the diverse ways in which they leave their mark on the cosmos. The Galaxy Zoo project has enabled countless discoveries by harnessing the collective efforts of volunteers from around the world. The story of Hani van Arkel highlights the potential for ordinary individuals to make extraordinary contributions to our understanding of the universe. The Phoenix Cluster, the universe's most powerful cooling flow. Located about 5.7 billion light-years from Earth, the Phoenix Cluster is a region of extremes. It contains thousands of galaxies, an immense reservoir of hot gas, and a central supermassive black hole. What sets the Phoenix Cluster apart from other galaxy clusters, however, is its unusually high rate of cooling and the effects this has on its central region. At the heart of the Phoenix Cluster lies a giant elliptical galaxy surrounded by a vast halo of gas. This gas, which makes up the bulk of the cluster's visible matter, is extremely hot, with temperatures reaching tens of millions of degrees. Normally, gas in galaxy clusters remains hot for billions of years, prevented from cooling by the energy emitted by the central black hole. In most clusters, the supermassive black hole produces jets and outflows that heat the gas and prevent it from cooling and condensing into stars. In the Phoenix Cluster, however, this balance appears to have broken down. Observations show that the gas in the cluster's core is cooling at an extraordinary rate, about 20 times faster than in most other clusters. This rapid cooling allows the gas to condense and form stars at a pace rarely seen in the universe. The central galaxy of the Phoenix Cluster is producing new stars at a rate of about 740 solar masses per year, one of the highest star formation rates ever observed in a galaxy cluster. For comparison, the Milky Way forms stars at a much more modest rate of 1 to 2 solar masses per year. The reasons behind the Phoenix cluster's extreme cooling flow remain a subject of intense study. One possibility is that the supermassive black hole at the center of the cluster is not producing enough energy to offset the cooling of the gas. This could be due to the black hole being in a relatively quiet phase of its activity cycle, allowing the gas to cool unchecked. Alternatively, the feedback mechanism may be working differently in the Phoenix cluster, with less efficient heating or a different distribution of energy. As the gas cools and condenses, it feeds a cycle of rapid star formation that transforms the central galaxy. The new stars are relatively young and massive, creating a vibrant and dynamic core surrounded by older, more evolved stars. As the gas cools and sinks toward the center of the cluster, it provides a fresh supply of material for the black hole to consume. This accretion process can fuel the black hole's activity, potentially triggering powerful outflows and jets that could eventually restore the balance between heating and cooling. However, the exact relationship between the cooling gas, star formation, and black hole activity in the Phoenix cluster is not yet fully understood. For decades, astronomers have relied on simulations and observations to develop a standard framework for understanding clusters. In most clusters, the interplay between cooling gas and black hole feedback creates a relatively stable system, with limited star formation and a predictable distribution of matter. The Phoenix cluster, with its extreme cooling and rapid star formation, defies this model, suggesting that galaxy clusters may be more diverse and dynamic than previously thought. The discovery of the Phoenix cluster has also raised questions about the role of magnetic fields, turbulence, and other physical processes in regulating the behavior of gas in clusters. For example, magnetic fields may play a role in shaping the flow of cooling gas, influencing how it condenses and forms stars. Turbulence within the cluster could affect the distribution of energy, creating localized regions of intense cooling. Understanding these processes requires detailed observations and simulations, as well as comparisons with other clusters that exhibit similar, though less extreme, behaviors. X-ray observations from NASA's Chandra X-ray Observatory have provided a detailed view of the hot gas in the cluster, revealing its temperature, density, and cooling rate. Optical and infrared observations have captured the burst of star formation in the central galaxy, while radio telescopes have probed the activity of the central black hole. Together, these data have painted a complex picture of a cluster in flux, where multiple processes interact in unexpected ways. Other clusters with rapid cooling flows and high star formation rates have been identified, though none match the extremes of the Phoenix cluster. By studying these systems, astronomers hope to determine whether the Phoenix cluster represents an outlier or is part of a broader class of objects. Lyman alpha blobs, enigmatic clouds in the early universe. Lyman alpha blobs are these massive clouds of hydrogen gas located billions of light years away, which emit intense Lyman alpha radiation, a specific wavelength of ultraviolet light. They were first discovered in the late 1990s during deep surveys of the sky, and their discovery raised more questions than answers. What powers these glowing clouds? Why are they so large? And what role do they play in the formation of galaxies? Some of these clouds stretch over hundreds of thousands of light years, making them larger than entire galaxies. Despite their size, they are faint and difficult to detect, requiring powerful telescopes and sensitive instruments to observe. Their light originates from the Lyman alpha emission line, which is produced when electrons in hydrogen atoms drop to their lowest energy state, releasing photons. This emission is common in the universe, particularly in regions of star formation, but the scale and intensity seen in Lyman alpha blobs are unusual. Several theories have been proposed to explain the powerful radiation they emit. One possibility is that they are powered by intense star formation within young galaxies embedded in the blobs. As massive stars form and die, they release large amounts of ultraviolet light, which can ionize the surrounding hydrogen gas. When the ionized gas recombines, it emits Lyman alpha photons, creating the glowing clouds we observe. Another theory suggests that Lyman alpha blobs are fueled by active galactic nuclei, or AGNs, powered by supermassive black holes. In this scenario, the black holes at the centers of galaxies accrete matter, releasing tremendous energy in the form of radiation and outflows. This energy can heat and ionize the surrounding gas, producing the characteristic Lyman alpha emission. Observations of some Lyman alpha blobs have revealed the presence of AGNs supporting this idea, but not all blobs show evidence of active black holes. A third possibility is that the radiation comes from cooling gas falling into massive halos of dark matter. In the early universe, large amounts of gas would have been pulled into the gravitational wells created by dark matter. As the gas fell inward, it would have heated up and then cooled, releasing energy in the form of Lyman alpha radiation. This cooling process could explain the diffuse and extended nature of the blobs, as well as their location in regions of intense galaxy formation. Lyman alpha blobs are often found in areas of the universe where galaxies are forming rapidly, such as galaxy clusters or protoclusters. These regions are rich in gas and dust, providing the raw materials for star and galaxy formation. The blobs may represent a stage in the evolution of these structures, acting as reservoirs of gas that feed the growth of galaxies. Over time, the gas in the blobs could condense into stars and planets, eventually forming the kinds of galaxies we see today. Because they are located so far away, their light has taken billions of years to reach us, allowing astronomers to see them as they were when the universe was much younger. This makes them valuable tools for studying the processes that shaped the first galaxies and large-scale structures. By analyzing the properties of the blobs, such as their size, luminosity, and chemical composition, researchers can learn more about the environment in which they formed. Many questions still remain unanswered. Why are Lyman alpha blobs so rare? Surveys of the sky have revealed only a few dozen of these objects, suggesting that they represent a brief and unusual phase in the life of galaxies or galaxy clusters. What triggers the formation of a Lyman alpha blob, and what determines its size and brightness? And how do they interact with their surroundings, influencing the growth of galaxies and the distribution of matter in the universe? Their large sizes and intense luminosities are difficult to reproduce in simulations, suggesting that our understanding of the processes that create and sustain these objects is incomplete. They may point to gaps in our knowledge of how gas behaves in the early universe, or they could reveal new phenomena that have yet to be explored. The Bootes Void, a hole in the universe. Located in the direction of the Bootes constellation, the Bootes Void is an immense cosmic void that stretches across an estimated 330 million light-years, double the size of the local void. It is one of the largest known empty regions in the observable universe. The void was first identified in 1981 by astronomers Robert Kirshner and his colleagues during a redshift survey of galaxies. As they mapped the distribution of galaxies, they noticed a startlingly empty region in their data, a gap far larger than anything previously observed. At first, it was difficult to grasp the scale of the void. It spans such a vast area that light would take hundreds of millions of years to cross it. Despite its apparent emptiness, the Bootes Void is not completely devoid of galaxies. Astronomers have identified a small number of galaxies within the void, though they are sparsely distributed compared to the denser regions of the universe. The density of galaxies in the void is so low that if the Milky Way were located there, the night sky would be almost entirely dark, with few stars visible to the naked eye. This stark contrast highlights just how unusual the void is when compared to the more typical regions of the universe. Most voids are much smaller and less pronounced, fitting more neatly into the framework of cosmic structure formation. The Boots void, by contrast, seems almost too large to have formed naturally within the universe's 13.8 billion-year history. This has led some researchers to propose alternative explanations for its formation. One possibility is that the void was created by the merging of smaller voids over time, a process known as void hierarchy. In this scenario, multiple smaller regions of low density could have coalesced into a single, larger void as galaxies and matter were pulled into denser regions nearby. Another hypothesis is that the Bootes void may be linked to the influence of dark energy. Dark energy affects the movement of matter on the largest scales, and it's possible that its influence has played a role in shaping the void. However, the exact relationship between dark energy and void formation remains poorly understood, as dark energy itself is still one of the great unknowns in modern physics. The few galaxies within the void are of particular interest to astronomers because they have evolved in relative isolation. Unlike galaxies in denser regions, which are influenced by frequent interactions and mergers, void galaxies have likely experienced fewer external disruptions. This isolation offers a unique perspective on galaxy formation and evolution, shedding light on how galaxies grow and change when left to develop on their own. Despite its name, the Bootes void is not entirely isolated from the rest of the universe. Its edges connect to the surrounding filaments of the cosmic web, where galaxies and clusters are more densely packed. These boundary regions are of particular interest because they represent the transition between the void and the more typical regions of the universe. Understanding how matter flows across these boundaries can provide insights into the dynamics of large-scale structures and the processes that shape them. The vast emptiness of the void serves as a stark reminder of the scale and complexity of the cosmos, where regions of intense activity coexist with areas of profound emptiness. It highlights the diversity of environments within the universe and underscores the importance of studying both the dense and empty regions to gain a complete understanding of cosmic evolution. Cosmic bubbles, the aftermath of quasar winds. Cosmic bubbles are immense structures made of hot gas that form as a result of intense winds and radiation emanating from quasars. The process that creates cosmic bubbles begins with the quasar's energetic output. The intense radiation and high-speed winds generated by the quasar interact with the surrounding gas, pushing it outward and creating a shell-like structure. These winds are incredibly powerful, often traveling at speeds of thousands of kilometers per second. As they sweep through the galaxy, they can clear out large amounts of gas and dust, carving out vast bubbles that extend far beyond the galaxy itself. Some bubbles span hundreds of thousands of light years, making them some of the largest structures associated with individual galaxies. Observations of these bubbles often reveal their glowing edges, where the hot gas interacts with the cooler, denser material around them. The heat generated by these interactions can reach millions of degrees, causing the gas to emit X-rays and other high-energy radiation. This makes cosmic bubbles visible to telescopes that can detect these wavelengths. By expelling gas from the central regions of galaxies, quasar winds can regulate star formation. Gas is a critical ingredient for star formation, as it serves as the raw material for new stars. When quasars push this gas outward, they deprive the galaxy's core of the resources needed to form stars, effectively shutting down star formation in that region. Many massive galaxies are thought to have gone through periods of quasar-driven quenching, which transformed them from active star-forming galaxies into the quieter, more stable systems we see today. As the quasar winds push gas outward, they can spread metals and other elements into the intergalactic medium. These elements, forged in the cores of stars and distributed by supernova explosions, are critical for the formation of future generations of stars and planets. By spreading these materials across vast distances, cosmic bubbles contribute to the enrichment of the universe, ensuring that the building blocks for new stars and planets are available in regions far from their original sources. The energy released by quasars and their winds can heat the surrounding gas, preventing it from cooling and collapsing into new galaxies. This regulates the growth of structures in the universe, ensuring that galaxies do not grow unchecked. Feedback mechanisms like this are a key component of modern cosmological models, as they help to explain the observed distribution of galaxies and the balance between dense clusters and empty voids. One of the challenges in studying them is their sheer scale. Because they are so large, it can be difficult to capture their full extent in observations. Additionally, the processes that drive their formation are complex and involve a range of physical phenomena, from the behavior of black holes to the dynamics of interstellar gas. Understanding these processes requires a combination of observational data, theoretical models, and computer simulations. As the bubbles expand, they eventually cool and slow down, becoming less energetic. At this point, they may begin to collapse back inward or merge with other structures. Observing these later stages of evolution is challenging, as the bubbles become harder to detect as they lose energy. Cosmic bubbles are not just limited to the local universe, they are also observed in distant galaxies, providing insights into the behavior of quasars in the early universe. Because light from distant objects takes time to reach us, observing these bubbles allows astronomers to look back in time and study how quasars and their winds influence galaxy formation billions of years ago. These observations reveal that quasar activity was much more common in the early universe, suggesting that cosmic bubbles played an even larger role in shaping the cosmos during its formative years. One particularly striking example of a cosmic bubble is found in the galaxy NGC 3079, where a massive bubble of hot gas extends over 5,000 light-years from the galaxy's core. This bubble, visible in X-ray and optical wavelengths, provides a detailed view of how quasar winds interact with the surrounding gas. Observations of NGC 3079 and similar systems have shown that the edges of these bubbles are sites of intense star formation as the compressed gas triggers the collapse of clouds into new stars. This highlights the dual role of quasar winds in both suppressing and stimulating star formation, depending on the conditions in the surrounding environment. The distribution of dark matter in a galaxy affects how gas is pulled in and expelled, influencing the size and shape of the bubbles. By comparing observations of cosmic bubbles with simulations that include dark matter, astronomers can test their models of how dark matter interacts with normal matter, helping to refine our understanding of dark matter's role in galaxy formation and evolution. The enigmatic CMB Cold Spot, an imprint of ancient voids. The cosmic microwave background, or CMB, is the faint glow of radiation left over from the Big Bang that stretches across the entire sky, offering a snapshot of the universe as it was around 380,000 years after its formation. It's remarkably uniform, with only slight temperature variations that represent density fluctuations in the early cosmos. These variations would later grow into the galaxies and large-scale structures we see today. However, amidst this near uniformity, there is a particularly strange and puzzling feature, the CMB Cold Spot. The CMB Cold Spot is an area of the sky where the temperature of the CMB is significantly lower than the surrounding regions. Discovered in 2004 using data from the Wilkinson Microwave Anisotropy Probe. This anomaly spans roughly 1.8 billion light-years and is about 70 microkelvins cooler than the average CMB temperature. While the difference in temperature might seem small, it is statistically significant and stands out starkly against the backdrop of the otherwise predictable variations in the CMB. The cold spot immediately caught the attention of cosmologists because it defied expectations. According to the standard model of cosmology, the variations in the CMB should follow a random Gaussian distribution. This means that while there are bound to be regions that are slightly hotter or cooler than average, a feature as pronounced and extensive as the cold spot is highly unlikely. Its existence has sparked a range of theories about its origin, each attempting to explain how such an anomaly could arise within the framework of our understanding of the universe. One of the most prominent explanations for the cold spot is the presence of a massive supervoid. Supervoids are not unheard of in the universe, they are part of the cosmic web. However, the supervoid hypothesized to explain the cold spot would need to be extraordinarily large, stretching across hundreds of millions of light-years, and significantly less dense than the average void. The idea is that such a supervoid could affect the CMB through a phenomenon known as the integrated Sachs-Wolf (ISW) effect. As photons from the CMB travel through a supervoid, they lose energy due to the gravitational influence of the void. Normally, a photon entering a gravitational well will gain energy on the way in and lose it on the way out, balancing out the overall effect. But in a supervoid, the expansion of the universe alters this balance, causing the photons to emerge with less energy than they had when they entered. This creates a cooler spot in the CMB, where the void is located. In 2015, astronomers identified a potential supervoid in the direction of the cold spot using data from galaxy surveys. This region, located about 3 billion light-years away, appears to be less dense than its surroundings, lending some support to the supervoid hypothesis. However, the observed void does not seem large or deep enough to fully account for the cold spot's size and temperature difference. This has left the door open for alternative explanations. Another possibility is that the cold spot is simply a rare but natural deviation from the expected distribution of temperature fluctuations in the CMB. While the probability of such a fluke occurring is low, it is not zero. Some cosmologists argue that with a large enough dataset, such anomalies are bound to appear purely by chance. If this is the case, the cold spot would not require any special explanation and would simply be an outlier in the random processes that shaped the early universe. Beyond these more conventional explanations, the cold spot has also inspired more speculative ideas. One possibility is that it could be a signal of interactions between our universe and another universe. In some models of cosmology, particularly those involving the multiverse hypothesis, our universe is just one of many that exist in a vast multiverse. If another universe came into contact with ours in the distant past, it could leave an imprint on the CMB, potentially explaining features like the cold spot. This idea is incredibly difficult to test, but it captures the imagination of those who wonder whether the cold spot could be a clue to something far grander than we currently understand. Another speculative idea involves the concept of exotic physics, phenomena that go beyond the standard model of cosmology and particle physics. For example, some theories suggest that the cold spot could be related to the decay of dark energy, or the influence of hypothetical particles that interacted with the early universe in unusual ways. Observing the CMB requires incredibly sensitive instruments, as the temperature variations are minuscule. Moreover, the region of the sky where the cold spot is located overlaps with the Milky Way's foreground emission, making it difficult to separate the signal from local noise. Despite these obstacles, advances in observational technology, such as the Planck satellite, have provided increasingly detailed data about the CMB and the cold spot, the Great Attractor, a mysterious pull in the universe. The universe is in constant motion, with galaxies traveling vast distances through space. Much of this movement is driven by the expansion of the universe itself, a consequence of the Big Bang. However, not all motion can be explained by expansion alone. Observations have revealed a puzzling gravitational anomaly, an unseen force pulling entire galaxies, including our own Milky Way, toward a particular region of space. This phenomenon is known as the Great Attractor. The story of the Great Attractor begins in the 1970s and 1980s, when astronomers were studying the motion of galaxies in the local universe. Using radio telescopes and optical surveys, they noticed something unusual. Galaxies in our cosmic neighborhood were not moving in a way that matched theoretical predictions. Instead of simply flowing outward with the universe's expansion, many galaxies appeared to be drawn toward a specific point in the sky, near the constellation Centaurus. This motion suggested the presence of a massive gravitational source, far larger than any individual galaxy or cluster. The discovery was surprising because the region toward which the galaxies are moving lies in a part of the sky obscured by the Milky Way's thick plain of stars, dust, and gas. This area, called the zone of avoidance, is difficult to observe with traditional optical telescopes. The dense material in our galaxy blocks much of the light from objects behind it, making it challenging to identify what might be causing such a powerful gravitational pull. Despite these obstacles, scientists have pieced together clues using other wavelengths of light, such as X-rays and radio waves, which can penetrate the galactic plane. Clusters like Norma and Centaurus, located near the suspected location of the anomaly, were found to contain vast numbers of galaxies and large amounts of mass. The combined gravitational influence of these clusters was thought to contribute to the observed motion of nearby galaxies. However, even when accounting for these known structures, the pull of the Great Attractor seemed far stronger than could be explained by the visible matter alone. Further observations suggested that the Great Attractor might not be a single object, but rather a complex region of space dominated by several massive structures. This includes galaxy clusters, dark matter, and possibly other unknown components. One particularly intriguing feature in the region is the Shapley supercluster, a massive collection of galaxies located about 650 million light-years away. The Shapley supercluster is one of the most massive structures in the known universe, containing enough mass to significantly influence the motion of galaxies over vast distances. Some scientists believe that the Shapley supercluster could be a key player in the Great Attractor's gravitational pull. Dark matter is believed to form the scaffolding for galaxy formation, creating vast networks of filaments and nodes where galaxies cluster together. In the case of the Great Attractor, it is likely that dark matter contributes significantly to the overall gravitational pull, even if it cannot be directly observed. The gravitational anomaly lies relatively close to the Milky Way in cosmic terms, only about 150 to 250 million light-years away. This is much closer than other well-known massive structures, such as the Shapley supercluster or the Sloan Great Wall. Despite its proximity, the Great Attractor remains shrouded in mystery because of its position behind the zone of avoidance. This has led some researchers to speculate that the anomaly might not be a single coherent structure, but rather a combination of several overlapping phenomena. One key concept in this field is the cosmic flow, the motion of galaxies and galaxy clusters driven by gravitational interactions. The Great Attractor is part of a larger pattern of motion in which galaxies are drawn toward regions of higher density, such as superclusters and voids. Understanding these flows helps scientists map the distribution of matter in the universe, including both visible and dark matter. Despite decades of research, the Great Attractor remains enigmatic. Advances in technology have provided new insights into this mysterious region. Instruments like the Parkes Radio Telescope and the Chandra X-ray Observatory have revealed previously hidden galaxy clusters and provided detailed maps of the zone of avoidance. These observations have helped refine our understanding of the Great Attractor's influence and its relationship to other massive structures in the universe. The Milky Way, along with the entire local group of galaxies, is moving toward the Great Attractor at a speed of approximately 600 kilometers per second. This motion is part of a larger flow known as the Laniakea supercluster, a vast region of space encompassing thousands of galaxies. The Great Attractor serves as one of the central points of gravitational influence within Laniakea, shaping the motion of galaxies across hundreds of millions of light-years. The Shapley supercluster, the heavyweight of the cosmos. Located approximately 650 million light-years away in the constellation Centaurus, the Shapley supercluster is a gravitational heavyweight, dominating the local universe in ways that challenge our understanding of cosmic structure. Its sheer scale and density make it a focal point for studying how matter clumps together on the largest scales and how these concentrations influence the motion of galaxies across vast distances. This supercluster contains thousands of galaxies, along with a significant amount of dark matter, gas, and other forms of mass that are not directly visible. When combined, these elements create an enormous gravitational field that affects not only the galaxies within the supercluster, but also those in its surrounding regions. The total mass of the Shapley supercluster is estimated to be more than 10 million billion times the mass of the Sun, making it one of the most massive known structures in the observable universe. In the 1930s, astronomer Harlow Shapley first identified the dense cluster of galaxies that now bears his name. Early observations revealed that this region contained an unusually high number of galaxies packed closely together. However, it wasn't until later, with the advent of more advanced telescopes and deeper surveys, that the true scale of the supercluster became apparent. By mapping the distribution of galaxies and their velocities, astronomers realized that the Shapley supercluster extended far beyond its core, forming a sprawling network of interconnected galaxy clusters and filaments. This structure is so massive that it plays a significant role in shaping the motion of galaxies over hundreds of millions of light-years. Galaxies in its vicinity, including those in the direction of the Great Attractor, are being drawn toward the Shapley supercluster. In fact, some researchers suggest that the Great Attractor itself may be part of a larger gravitational flow directed toward Shapley. This has led to the idea that the Shapley supercluster is not just a local feature, but a dominant force in the broader Laniakea supercluster. While the Great Attractor was initially thought to be the primary source of the anomalous motion of galaxies in our region of the universe, more recent observations have highlighted the role of Shapley as a secondary or even dominant contributor. This has shifted the focus of many studies toward understanding how these two massive structures interact and how their combined gravitational pull affects the overall dynamics of the local universe. Within its dense environment, galaxies are subject to intense gravitational interactions, including mergers and tidal forces. These processes can trigger bursts of star formation, alter the shapes and sizes of galaxies, and even strip away gas, leaving galaxies depleted of the material needed to form new stars. Its gravitational pull affects the motion of galaxies across vast regions of space, while its dense environment provides a laboratory for studying galaxy interactions and evolution. As telescopes and observational techniques continue to improve, scientists are uncovering more about this colossal structure and its role in the grand tapestry of the universe. The Pillars of Creation, star nurseries in infrared. The Pillars of Creation are one of the most iconic images of the cosmos. These towering columns of gas and dust are located within the Eagle Nebula, about 6,500 light-years away in the constellation Serpens. They are named for their role in creating new stars, acting as nurseries where dense pockets of gas collapse under gravity to ignite nuclear fusion. For decades, they have symbolized the beauty and mystery of star formation, but recent infrared observations have revealed even more about the dynamic processes occurring within these celestial structures. When the Hubble Space Telescope first imaged the Pillars of Creation in 1995, the stunning detail of the visible light image brought them into focus. The image showed vast columns of interstellar gas and dust sculpted by the intense radiation and winds from nearby massive stars. These winds, moving at incredible speeds, strip away the less dense material, leaving behind the denser regions that resist erosion. The tips of these pillars contain the densest clumps of material, where stars are actively forming. These evaporating gaseous globules, or EGGs, are small pockets of gas and dust that are shielded from the destructive forces around them, allowing star formation to proceed. While visible light provides a breathtaking view, it is limited in what it can reveal about the internal structure of the pillars. The dense gas and dust that form the pillars block much of the light, hiding the processes occurring deep within. Infrared images of the pillars reveal a very different perspective. The once opaque columns become semi-transparent, showing intricate networks of gas filaments and embedded young stars. These stars, often in their earlier stages of development, are difficult to detect in visible light. Infrared observations, however, reveal their warm glow, highlighting the intense activity within the pillars. Some of these stars are just beginning to ignite nuclear fusion, while others are still in the process of gathering material from their surroundings. The star formation within the pillars of creation is a slow and complex process. Dense regions of gas collapse under their own gravity, forming protostars. As these protostars grow, they accumulate more material from the surrounding cloud, increasing their mass and temperature. Eventually, the core temperature becomes high enough for hydrogen atoms to fuse into helium, releasing energy and marking the birth of a new star. This process is not uniform, and the environment within the pillars plays a crucial role in shaping the stars that form. The intense radiation and winds from nearby massive stars can compress the gas in some areas, triggering star formation, while simultaneously eroding material in other regions, halting the process. While they appear static in images, they are constantly evolving. The intense radiation and winds from nearby stars are gradually eroding the pillars, dispersing their material into space. Infrared observations show evidence of this ongoing erosion, with streams of gas and dust being blown away from the tips of the pillars. This process, while destructive, also contributes to the cycle of star formation by redistributing material that can eventually coalesce into new stars and planetary systems. Infrared spectroscopy, which analyzes the light emitted or absorbed by molecules, has revealed the presence of complex organic molecules within the pillars. These molecules, which include carbon-based compounds, are the building blocks of life as we know it. Their presence in the pillars of creation highlights the potential for similar regions in the galaxy to serve as cradles for the formation of life. The pillars of creation are not isolated structures. They are part of a larger region of star formation within the Eagle Nebula. This region, known as a stellar nursery, contains numerous other areas where stars are forming. Infrared observations have revealed the connections between the pillars and their surrounding environment, showing how material flows between different regions. These flows of gas and dust create a dynamic and interconnected network, where the birth of one star can influence the formation of others. The intense radiation and winds that are eroding the pillars will eventually destroy them, dispersing their material into space. This process, however, takes time, and the pillars will likely continue to exist for tens of thousands of years. During this time, they will continue to serve as a site of active star formation, producing new generations of stars that will carry on the cycle of cosmic creation. The Red Square Nebula, the most symmetrical nebula ever found. Located about 5,000 light-years away in the constellation Serpens, the Red Square Nebula has captured the attention of astronomers not just for its vivid red glow, but for its astonishingly precise symmetry. Unlike most nebulae, which display irregular, chaotic shapes, the Red Square Nebula exhibits a near-perfect square shape, with a striking X pattern at its center. At the heart of the Red Square Nebula lies a star known as MWC 922. This star, believed to be nearing the end of its life, is shedding its outer layers into space, creating the surrounding nebula. This process is not unusual. Many dying stars eject material into space, forming planetary nebulae or other types of gas clouds. What sets the Red Square Nebula apart is the way this material has arranged itself into a symmetric pattern. The X shape seen in images of the nebula is thought to result from light escaping through two opposing cones of gas and dust, creating a mirrored effect. Astronomers first discovered the Red Square Nebula using ground-based telescopes. The symmetry of the nebula became apparent when researchers analyzed the light it emitted, revealing a series of nested squares that extend outward from the central star. These squares are not just visually striking, but also scientifically significant, as they suggest a high degree of order in the processes shaping the nebula. One possible explanation for the symmetry of the Red Square Nebula is the presence of a companion star. If MWC 922 is part of a binary system, the gravitational interaction between the two stars could influence the way material is ejected. A companion star could create periodic outflows of gas and dust, which would then expand outward in a symmetrical pattern. This hypothesis is supported by observations of other nebulae with similar, though less pronounced, symmetry, where binary systems have been confirmed. Another factor contributing to the nebula's shape could be the role of magnetic fields. Strong magnetic fields around MWC 922 might channel the ejected material into specific directions, creating the observed cones of light and gas. Magnetic fields are known to play a role in shaping other astronomical phenomena, such as jets emitted by young stars or the accretion disks around black holes. However, the exact nature and strength of the magnetic fields around MWC 922 remain uncertain, leaving this as an avenue for further research. Its vivid red hue is primarily due to hydrogen gas, which emits red light when it is ionized by the intense radiation from the central star. This ionization process is common in many nebulae, but the uniformity of the color in the Red Square Nebula adds to its symmetrical appearance. The interplay of light and gas within the nebula creates a mesmerizing effect, as the red glow is scattered and reflected by the surrounding dust, enhancing the visibility of the X pattern. The Red Square Nebula's symmetry and structure challenges the assumption that most nebulae are irregular and chaotic, suggesting that under certain conditions, highly ordered structures can emerge. This has led scientists to re-evaluate the factors that influence nebula formation, including the roles of binary systems, magnetic fields, and stellar rotation. Few nebulae exhibit such a high degree of symmetry, making it a valuable case study for astronomers. By studying the Red Square Nebula, scientists hope to gain insights into the final stages of stellar evolution, particularly for stars like MWC 922. Understanding how stars shed their outer layers and how this material interacts with the surrounding environment is crucial for building a more complete picture of the life cycle of stars. Are there specific types of stars or environments that favor this kind of structure, or is the Red Square Nebula a rare exception? To answer these questions, astronomers are searching for other nebulae with similar characteristics. While a few candidates have been identified, none match the Red Square Nebula's precision and clarity, highlighting its uniqueness. Despite the progress made in studying the Red Square Nebula, many mysteries remain. For example, the exact mechanism behind the X pattern is still not fully understood. While the theory of opposing cones of light and gas is widely accepted, the factors that create and maintain such a precise arrangement are not entirely clear. The Red Square Nebula also invites comparisons with other symmetric structures in space, such as the Egg Nebula or the Homunculus Nebula surrounding Eta Carinae. These objects share some similarities with the Red Square Nebula, such as the presence of bipolar outflows or interactions within binary systems. By studying these and other related objects, astronomers hope to identify common patterns and processes that can explain the formation of symmetric nebulae. Iris 20,324 plus 4,057, the Tadpole Nebula's mysterious tale. Iris 20,324 plus 4,057, often called the cosmic caterpillar or tadpole, is a striking cosmic structure with a peculiar elongated shape. Resembling a tadpole with a prominent head and a trailing tail, this nebula stands out among the vast array of celestial objects due to its unique form and the processes shaping it. Located approximately 4,600 light-years away in the constellation Cygnus, the caterpillar is part of a region rich in star formation and activity. The cosmic caterpillar is classified as a protostellar object, meaning it is in the early stages of star formation. At its core lies a dense region of gas and dust, where new stars are beginning to emerge. These protostars are still gathering material from the surrounding nebula. As they grow, their intense radiation and stellar winds influence the shape of the surrounding gas, contributing to the elongated structure that gives the nebula its name. One of the most striking features of the cosmic caterpillar is its tail, a long, narrow stream of gas and dust that extends outward from the central region. This tail is thought to be the result of powerful stellar winds and radiation from nearby massive stars. These stars emit a continuous flow of charged particles and high-energy radiation, which can strip away material from smaller, less dense regions of gas and dust. In the case of the tadpole, this process has sculpted the tail, giving it its characteristic shape. The nearby stars responsible for this sculpting are part of a larger stellar cluster, home to some of the most massive and luminous stars in the galaxy. These stars, known as O-type stars, are among the hottest and most energetic in existence. Their intense radiation creates a harsh environment, capable of eroding and reshaping surrounding gas clouds. The head of the cosmic caterpillar, where the protostar resides, acts as a shield, protecting some of the material from being blown away. This interaction between the nebula and the cluster's stars creates a dynamic and evolving structure. The process shaping the cosmic caterpillar is an example of a phenomenon known as radiation pressure and photoevaporation. Radiation pressure occurs when the photons emitted by massive stars exert a force on surrounding particles, pushing them away. Photoevaporation, on the other hand, involves the ionization of gas by high-energy radiation, causing the gas to heat up and disperse into space. Together, these processes carve out the tail and influence the nebula's overall appearance. The dense core at the head of the nebula contains a protostar still in the process of accumulating material. Observations of this region reveal complex interactions between gravity, radiation, and magnetic fields. As the protostar gathers mass, it emits its own stellar winds and radiation, adding another layer of complexity to the forces shaping the nebula. Understanding these processes can provide insights into how stars like our Sun form and evolve. Infrared observations of the Tadpole Nebula have been particularly useful in uncovering its secrets. These observations have shown that the nebula contains a mix of hydrogen, helium, and heavier elements, along with dust grains made of silicates and carbon compounds. This composition is typical of star-forming regions and reflects the material left behind by previous generations of stars. The elongated shape of the cosmic caterpillar is not entirely unique, but is part of a broader category of structures known as cometary globules. These globules share similar characteristics, with dense, rounded heads and trailing tails of gas and dust. They are often found in regions of active star formation, where the influence of massive stars can create these distinctive shapes. Despite its similarities to other structures, the cosmic caterpillar has features that make it stand out. For one, its tail is exceptionally long and well-defined, suggesting a particularly strong interaction with the surrounding environment. Additionally, the protostar at its core appears to be at a critical stage of development, making it an ideal candidate for studying the transition from a protostellar core to a fully fledged star. The cosmic caterpillar's location in the Cygnus region places it in one of the galaxy's most active star-forming areas. This region, known as the Cygnus X complex, is home to numerous massive stars, nebulae, and clusters. The high level of activity in this area creates a dynamic environment where interactions between stars and gas clouds are common. The Tadpole Nebula is just one of many fascinating objects in this region, but its unique shape and early stage of star formation make it a standout. While massive stars exert a powerful influence on their surroundings, the nebula's dense core resists these forces, preserving the conditions necessary for star formation. This balance between destruction and creation is a recurring theme in astrophysics, highlighting the interconnectedness of cosmic processes. The Egg Nebula, a cosmic light show in transition. The Egg Nebula, formerly known as CRL 2688, is a stunning example of a celestial object caught in a moment of transition. Located approximately 3,000 light-years away, this nebula is a dying star in the process of shedding its outer layers, preparing to transform into a planetary nebula. Its name comes from its appearance, which resembles an egg surrounded by radiant layered shells of gas and dust. At the heart of the egg nebula lies a star nearing the end of its life. This star, once similar to our Sun, has exhausted the nuclear fuel in its core and is shedding its outer layers into space. This phase of stellar evolution is known as the asymptotic giant branch, or AGB stage, during which stars become unstable and begin to lose mass at an accelerated rate. The material ejected from the star forms the glowing shells of gas and dust that surround the nebula. The most captivating feature of the egg nebula is its appearance. Observations show a series of concentric arcs or rings radiating outward from the central star. These arcs are thought to be created by periodic pulses of mass loss from the dying star, with each pulse producing a new layer of material. The arcs are illuminated by the star's light, which is scattered by the dust, creating the nebula's soft, glowing effect. The symmetry and regularity of these arcs give the egg nebula its characteristic shape, making it one of the most photogenic objects in the night sky. Adding to the nebula's dramatic appearance are two bright beams of light emerging from opposite sides of the central star. These beams, often described as searchlights, are produced by starlight escaping through gaps in the surrounding dust. The dust forms a thick, disc-like structure around the star, blocking light in most directions and allowing it to shine through only along specific paths. The result is a striking bipolar shape, with the beams illuminating the nebula and creating a cosmic light show. The egg nebula's intricate structure provides valuable clues about the processes occurring during the final stages of a star's life. For example, the regularity of the arcs suggests that the mass loss events are periodic, possibly driven by changes in the star's internal dynamics or interactions with a companion star. Many stars in the AGB stage are part of binary systems where the presence of a second star can influence the behavior of the dying star, shaping the ejected material and creating the symmetrical patterns seen in objects like the egg nebula. The dust is made up of tiny solid particles, including silicates and carbon-based compounds, that condense from the material ejected by the star. Over time, this dust will be carried away by stellar winds, enriching the surrounding interstellar medium with the elements needed for the formation of new stars and planets. The dust surrounding the star absorbs visible light and re-emits it at longer wavelengths. Instruments like the Hubble Space Telescope and the Spitzer Space Telescope have provided detailed images of the nebula, revealing its layered structure and the properties of its dust. These observations have shown that the dust is rich in complex molecules, including hydrocarbons, which are essential building blocks for life. The transformation of the egg nebula into a planetary nebula is still underway. Over the next few thousand years, the central star will continue to shed its outer layers, creating more shells of gas and dust. Eventually, the star will expose its hot, dense core, known as a white dwarf. The intense radiation from the white dwarf will ionize the surrounding gas, causing it to glow and forming a classic planetary nebula. This stage will mark the final phase of the star's evolution before it fades into obscurity. In about 5 billion years, the Sun will enter the AGB stage, shedding its outer layers and creating a planetary nebula of its own. While the exact appearance of the Sun's nebula is uncertain, objects like the egg nebula provide a glimpse into the processes that will shape its final years. Studying these objects helps astronomers understand the life cycles of stars and the impact they have on their surroundings. The egg nebula's beauty and complexity make it a favorite target for both professional astronomers and amateur stargazers. Its distinctive shape and vibrant colors have made it a popular subject for astrophotography, capturing the imagination of people around the world. The Fibonacci spiral in galaxy formation. In the vast expanse of the cosmos, surprising patterns sometimes emerge. One such pattern is the Fibonacci spiral, a mathematical concept that seems to manifest in the structure of spiral galaxies. These galaxies, characterized by their sweeping spiral arms, are striking in their appearance. The connection between their structure and the Fibonacci sequence is a fascinating intersection of mathematics and astrophysics. The Fibonacci sequence is a series of numbers where each number is the sum of the two preceding ones: 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on. When these numbers are translated into a spiral pattern, the result is a curve that grows wider as it moves outward, but at a consistent rate. This curve, often called the golden spiral, is observed in many natural phenomena, from the arrangement of sunflower seeds to the shape of hurricanes. In spiral galaxies, this same pattern can be seen in the way their arms wind around the galactic core. The arms of spiral galaxies are not solid structures. They are regions of higher density that move through the galaxy like ripples in a pond. These arms are rich in gas, dust, and young stars, making them some of the most dynamic and active areas of a galaxy. The spiral shape arises from a process known as density wave theory. According to this theory, gravitational interactions within the galaxy create waves of higher density that propagate through the disk. As material moves through these waves, it is compressed, triggering star formation and giving the arms their bright glowing appearance. Observations of spiral galaxies show that the pitch angle of their arms, the angle between the arm and the circle it forms around the center, often aligns with the growth rate of the Fibonacci spiral. This alignment suggests that the same mathematical principles that govern the Fibonacci sequence may also influence the structure of galaxies. While not all spiral galaxies perfectly match the golden spiral, the resemblance is close enough to raise intriguing questions about the underlying forces at work. Gravity, the dominant force in galaxy formation, operates in predictable ways, creating structures that reflect its influence. The spiral arms are a product of the balance between gravitational attraction and the motion of stars and gas within the galaxy. This balance creates patterns that are not only functional, but also aesthetically pleasing, echoing the beauty of mathematical order. The same sequence that describes the growth of a nautilus shell or the arrangement of leaves on a stem can also describe the structure of a galaxy spanning hundreds of thousands of light years. This universality suggests that mathematics is not just a tool for understanding the universe, but a fundamental part of its fabric. The Fibonacci sequence, in particular, seems to act as a bridge between the microscopic and the cosmic, linking the smallest scales of nature to the largest. By understanding the patterns of galaxy formation, astronomers can gain insights into the history and evolution of the universe. Spiral galaxies are some of the most common types of galaxies, and their structure provides clues about the processes that shaped them. For example, the spacing of the arms can reveal information about the density of the galaxy's disk and the speed at which stars and gas move within it. If the spiral patterns align with the predictions of density wave theory, it supports the idea that these waves play a central role in shaping galaxies. Conversely, any deviations from the expected pattern can point to additional factors, such as interactions with neighboring galaxies or variations in the distribution of dark matter. By studying these patterns, astronomers can refine their models and deepen their understanding of the universe. The symmetry and elegance of spiral galaxies have long captured the imagination of astronomers and the public alike. The realization that their shape reflects a mathematical pattern adds another layer of wonder, showing how the universe combines order and complexity in ways that are both functional and beautiful. For many, the Fibonacci spiral in galaxies serves as a reminder of the harmony between science and art, revealing the beauty of the cosmos through the lens of mathematics. Not all spiral galaxies conform to the same pattern, and some have arms that are tightly wound, while others are more loosely coiled. These variations depend on factors such as the galaxy's mass, rotation rate, and history of interactions with other galaxies. By comparing the structures of different spiral galaxies, astronomers can identify the factors that influence their shape and determine how closely they align with the Fibonacci spiral. The cosmic fingerprint. Patterns in the cosmic microwave background. The CMB is a remnant of the Big Bang, a snapshot of the cosmos as it was roughly 380,000 years after its birth. At that time, the universe had cooled enough for atoms to form, allowing light to travel freely for the first time. The patterns imprinted on the CMB are like a cosmic fingerprint, holding valuable information about the universe's earliest moments and its subsequent evolution. These patterns appear as tiny fluctuations in temperature and density, visible as variations in the intensity of the CMB radiation. Although the CMB has an average temperature of about 2.73 Kelvin, it contains slight differences in temperature on the order of microkelvins. These differences are not random. Instead, they reflect the distribution of matter and energy in the early universe, shaped by processes that occurred just moments after the Big Bang. The patterns in the CMB are the result of sound waves rippling through the hot plasma that filled the early universe. These sound waves, or acoustic oscillations, were created by the interplay of gravity and radiation. Regions of higher density experienced stronger gravitational pull, compressing the plasma and heating it up. Meanwhile, radiation pressure pushed matter outward, creating rarefied regions. This back-and-forth motion generated a series of ripples, leaving imprints on the CMB that scientists can now observe. When the CMB was first detected, it was nearly the same temperature in every direction, confirming the idea that the universe was once in a hot, dense state. However, the small fluctuations in the CMB reveal crucial details about the seeds of structure in the universe. These tiny variations in density were the precursors to the galaxies, clusters, and other large-scale structures we see today. Over billions of years, gravity amplified these small differences, pulling matter together to form the cosmic web. To study the CMB in detail, scientists use sensitive instruments aboard satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite. These missions have provided increasingly detailed maps of the CMB, allowing researchers to measure its fluctuations with unprecedented precision. The resulting maps reveal a rich tapestry of patterns, each one containing a wealth of information about the early universe. The fluctuations occur at different sizes, ranging from tiny spots to large patches across the sky. By analyzing the distribution of these scales, scientists can infer important properties of the universe, such as its age, composition, and geometry. For example, the largest scale fluctuations provide clues about the overall curvature of the universe, indicating whether it is flat, open, or closed. Observations of the CMB strongly suggest that the universe is flat, consistent with the predictions of the standard cosmological model. In addition to variations in temperature, the CMB contains subtle patterns of polarization, which arise from the way light scattered off free electrons in the early universe. These polarization patterns come in two types: E modes and B modes. E modes are associated with density fluctuations, while B modes are linked to the twisting effects of gravitational waves. Detecting B modes in the CMB is a major goal of cosmology, as they could provide direct evidence for the rapid expansion of the universe during a period known as inflation. Inflation is a key part of the standard model of cosmology, proposing that the universe underwent an extremely brief but dramatic period of expansion just fractions of a second after the Big Bang. This expansion would have smoothed out any initial irregularities in the universe, explaining the overall uniformity of the CMB. The patterns in the CMB are consistent with this picture, offering strong support for the theory of inflation. However, some features of the CMB remain mysterious. One of these is the so-called cold spot, a region of the sky where the CMB temperature is significantly lower than expected. The CMB also contains evidence of subtle anomalies that deviate from the predictions of the standard cosmological model. For example, Some studies have found hints of a preferred direction in the CMB, which could suggest that the universe has a slight asymmetry. If confirmed, these anomalies could point to new physics beyond the current understanding of the universe, challenging long-held assumptions about its isotropy and homogeneity. Despite these uncertainties, the CMB remains one of the most powerful tools for studying the early universe. Its patterns offer a unique window, providing insights that are impossible to obtain through other means. By continuing to study the CMB with greater precision, scientists hope to uncover even more details about the origins and evolution of the cosmos. The giant radio galaxy Alcyoneus, a cosmic colossus. The universe is filled with objects of staggering proportions, but even among these giants, some stand out as extraordinary. Alcyoneus, one of the largest known radio galaxies, is one such colossus. Discovered relatively recently, this cosmic giant spans an unimaginable distance, stretching millions of light-years across. Radio galaxies are a special type of galaxy characterized by the emission of powerful radio waves. These waves are generated by jets of charged particles traveling at nearly the speed of light, propelled outward from the galaxy's core. At the heart of these galaxies lies a supermassive black hole, millions or even billions of times the mass of the Sun. As matter falls into the black hole, it forms a swirling disk, generating intense energy that powers the jets. These jets extend far beyond the galaxy itself, interacting with the surrounding environment and forming massive structures known as radio lobes. Alcyoneus was identified using data from the Low Frequency Array, or LOFAR, a network of radio telescopes spread across Europe. LOFAR is designed to detect low-frequency radio emissions, making it ideal for observing the vast structures created by radio galaxies. When astronomers analyzed the data, they discovered Alcyoneus, a galaxy whose radio lobes extend over 16 million light-years, making it the largest known radio galaxy at that time. To put this into perspective, if Alcyoneus were placed in our galaxy's vicinity, its lobes would stretch well beyond the local group, the collection of galaxies that includes the Milky Way. How can a galaxy grow to such immense proportions? Scientists believe that the size of a radio galaxy depends on several factors, including the activity of its central black hole, the density of the surrounding environment, and the age of the radio lobes. Alcyoneus may have a particularly powerful black hole, capable of sustaining jets for millions of years. Alternatively, its environment may be unusually sparse, allowing the jets to expand without significant resistance. The lobes of Alcyoneus are not merely empty regions of space. They are filled with charged particles and magnetic fields, which emit radio waves as they interact. These lobes are visible because they glow in the radio spectrum, providing a map of the galaxy's influence on its surroundings. By studying the structure and composition of these lobes, astronomers can learn about the processes that govern the interaction between galaxies and the intergalactic medium. The activity of a black hole is not constant. It can go through cycles of activity and dormancy. The size and shape of the radio lobes can provide clues about the duration and intensity of these active phases. In the case of Alcyoneus, its immense lobes suggest a long period of sustained activity, during which the black hole expelled enormous amounts of energy into its surroundings. The jets and lobes of radio galaxies can heat the surrounding gas, preventing it from cooling and forming new stars. Alcyoneus, with its enormous size, may represent an extreme example of this feedback process, providing valuable insights into how galaxies influence their surroundings on the largest scales. Despite its size, Alcyoneus is surprisingly faint in the optical spectrum. This faintness suggests that the galaxy itself may not be particularly massive or luminous compared to other radio galaxies. Instead, its extraordinary size may be due to other factors, such as the efficiency of its jets or the properties of its environment. This observation challenges the assumption that the largest radio galaxies must also be the most massive or powerful, highlighting the need for further research to understand the factors that determine their size. The study of Alcyoneus is still in its early stages. Astronomers are working to determine the precise mechanism that drives the jets and sustains their energy over such vast distances. They are also investigating the role of magnetic fields in shaping the structure of the lobes and the interactions between the jets and the surrounding medium. The Galactic X, the Milky Way's mysterious bulge. At the heart of the Milky Way lies the Galactic X. This peculiar X-shaped feature is embedded within the central bulge of our galaxy, a densely packed region of stars, gas, and dust. While it may not be immediately visible to the naked eye, modern observations using infrared telescopes have revealed its distinct shape. The bulge itself is a spheroidal region of stars that surrounds the galactic center, stretching thousands of light-years across. Unlike the flat disk of the Milky Way, which contains most of its spiral arms, the bulge is more three-dimensional, with stars moving in complex orbits. This region is thought to have formed early in the galaxy's history, making it a sort of fossilized record of the Milky Way's ancient past. The X-shaped structure was first hinted at in data from infrared surveys, which can penetrate the thick clouds of dust that obscure the galactic center in visible light. Infrared observations revealed that the bulge is not uniformly shaped, but has a bar-like structure extending across it. This bar, in turn, appears to split into two diagonal arms, forming an X when viewed from certain angles. The feature became more apparent in subsequent studies, confirming its presence and prompting further investigation. The bar is a long, elongated feature made up of stars and gas, extending from the central bulge out into the disk of the galaxy. Bars are not uncommon in spiral galaxies, and they play a significant role in redistributing material within a galaxy. In the case of the Milky Way, the bar's rotation and gravitational influence appear to have shaped the bulge into its current form, including the X-shaped structure. One leading theory suggests that the Galactic X is a result of what is known as a boxy/peanut-shaped bulge. This type of bulge forms when a bar undergoes a process called vertical buckling. As the bar rotates, gravitational forces cause some of its stars to move out of the plane of the galaxy, creating a more three-dimensional structure. Over time, the bar's shape evolves, and the vertical motions of stars create the appearance of an X when viewed from certain perspectives. This theory is supported by computer simulations of galaxy dynamics, which produce similar structures under the right conditions. The presence of the Galactic X confirms the importance of the bar in shaping the central regions of the galaxy. Bars are thought to drive the flow of gas and stars toward the galactic center, fueling star formation, and potentially feeding the supermassive black hole at the core. By studying the Galactic X, astronomers can better understand how these processes have unfolded over billions of years. The shape and orientation of the Galactic X are influenced by the underlying gravitational potential of the galaxy, which is determined by the combined mass of stars, gas, and dark matter. By analyzing the motions of stars within the bulge, scientists can infer the distribution of mass and test models of the galaxy's structure. This, in turn, helps refine our understanding of the Milky Way's overall composition and dynamics. Similar structures have been observed in other barred spiral galaxies, suggesting that this phenomenon may be a common outcome of galactic evolution. By comparing the Milky Way's bulge to those of other galaxies, astronomers can identify patterns and differences that shed light on the factors influencing their development. The central bulge is a bustling region of activity, with high densities of stars, intense radiation, and complex interactions between gas and dust. The gravitational influence of the X-shaped structure could affect the motions of stars and gas within the bulge, potentially shaping the formation of new stars or altering the trajectories of existing ones. Understanding these effects is an ongoing area of research, with implications for the dynamics of the entire galactic center. Observing the galactic center is notoriously difficult due to the thick clouds of gas and dust that block visible light. Infrared and radio telescopes have been crucial in unveiling the hidden features of this region, allowing astronomers to map the distribution of stars and gas in unprecedented detail. As technology continues to improve, future observations may reveal even more about the galactic X and its role in the Milky Way's story. One of the most exciting aspects of studying the galactic X is its potential to inform our understanding of the supermassive black hole at the galaxy's core, known as Sagittarius A*. This black hole, with a mass of about 4 million suns, exerts a powerful influence on its surroundings. The flow of material towards Sagittarius A* is shaped by the dynamics of the bulge and the bar, including the galactic X. By studying these interactions, astronomers can gain new insights into the relationship between black holes and their host galaxies, a key question in modern astrophysics. Odd radio circles, a new cosmic mystery. First identified in 2019, odd radio circles, or AURCs, are peculiar, faintly glowing rings of radio emission that do not resemble any previously known celestial structures. Their discovery has raised a host of questions about their origin, nature, and potential implications for our understanding of the universe. These enigmatic circles, which appear massive in size and have no obvious counterparts in other wavelengths of light, challenge astronomers to think beyond established frameworks. The story of AURCs began with the Australian Square Kilometre Array Pathfinder, or ASKP, a powerful radio telescope designed to survey large areas of the sky with unprecedented sensitivity. During one of its initial deep sky surveys, astronomers noticed something unusual: several faint circular structures that didn't match the characteristics of any known astronomical objects. These circles, each several 100,000 light-years in diameter, were neither aligned with any visible galaxies, nor consistent with well-studied phenomena like supernova remnants or radio lobes from active galaxies. What makes AURCs particularly puzzling is their lack of emission in other parts of the electromagnetic spectrum. Unlike many celestial objects that emit light across multiple wavelengths, AURCs are detectable only in the radio band. Optical, X-ray, and infrared observations have yet to reveal any corresponding features, leaving astronomers to wonder what could produce such isolated radio emissions. This absence of multi-wavelength counterparts rules out many conventional explanations and hints at an entirely new category of phenomena. One of the leading hypotheses is that AURCs might be the remnants of enormous explosions or energetic events in distant galaxies. Such events could include powerful jets or outflows from supermassive black holes, which might produce large expanding shells of material visible as radio circles. In this scenario, the AURCs would represent shockwaves propagating through the intergalactic medium, much like ripples spreading out from a stone dropped into water. However, this idea raises further questions about the scale and energy of these events, as the size of AURCs suggests they are much larger than typical black hole-driven outflows. When galaxies collide or merge, they can create shockwaves and disturbances in the surrounding medium, potentially producing large-scale radio emissions. If AURCs are associated with such interactions, they might provide new insights into the dynamics of galaxy formation and evolution. However, the lack of visible galaxies at the centers of most AURCs complicates this explanation, as it suggests that any associated galaxies are either extremely faint or located at vast distances. In astronomy, circular structures often indicate symmetry, which can arise from processes like explosions, waves, or gravitational interactions. For example, supernova remnants are often roughly circular because the energy from the explosion spreads out uniformly in all directions. Similarly, the spherical shock waves produced by powerful gamma-ray bursts might appear as circles when observed from certain angles. If AURCs are indeed spherical structures, their radio emissions might represent just a thin slice of a much larger three-dimensional phenomenon. Some researchers have speculated that AURCs could be linked to dark matter or other exotic forms of energy. Dark matter could theoretically interact with ordinary matter in ways that produce radio emissions. Alternatively, orcs might represent the remnants of hypothetical cosmic events, such as the decay of massive particles or the collisions of topological defects in the fabric of space-time. While these ideas are highly speculative, they highlight the potential for orcs to reveal new physics beyond the standard models of cosmology and particle physics. To date, only a handful of orcs have been identified, making them rare but not unique. Their distribution across the sky suggests they are not confined to any specific region or structure, which could mean they are a common but faint phenomenon that has gone unnoticed until now. As radio telescopes like ASCAP and the Meerkat Array continue to survey the sky, astronomers hope to find more orcs and build a statistical sample large enough to discern patterns in their properties and distribution. Some researchers have proposed that orcs might be relics of processes that occurred billions of years ago during the epoch of galaxy formation. If this is the case, studying orcs could provide a unique window into the conditions and events that shaped the cosmos in its infancy. For example, orcs might be linked to the large-scale structures of the universe, such as cosmic filaments or voids, which could amplify and channel radio emissions over vast distances. Observing such faint and diffuse objects requires highly sensitive instruments and sophisticated data analysis techniques. Radio telescopes must sift through vast amounts of data to detect the weak signals from orcs, often requiring weeks or months of processing. Despite these difficulties, the study of orcs exemplifies the power of modern radio astronomy to uncover previously hidden aspects of the universe. It is possible that similar objects have been observed in the past, but were not recognized as distinct phenomena due to limitations in data quality or interpretation. By revisiting archival data from older radio surveys, researchers may uncover additional examples of orcs or related structures, helping to piece together their origin and nature. Fast radio bursts, signals from the distant universe. Fast radio bursts, or FRBs, are fleeting but incredibly powerful bursts of radio waves that originate from distant regions of the universe, often billions of light-years away. They last only milliseconds, yet during that brief moment, they can outshine entire galaxies in the radio spectrum. Since their discovery in 2007, FRBs have sparked intense curiosity and debate among scientists, as their origins and mechanisms remain largely unknown. The first FRB was discovered somewhat by accident. Astronomers analyzing data from the Parkes Radio Telescope in Australia found an unusually strong and brief pulse of radio waves that didn't match any known source. This burst, later named FRB 010724, became the prototype for what would eventually be recognized as a new class of astrophysical events. At first, some researchers speculated that the signal might have been caused by interference from Earth-based sources, such as satellites or electronic equipment. However, the extreme dispersion of the signal, which measures how radio waves are delayed as they travel through intergalactic space, suggested that the burst originated from far beyond our galaxy. Since then, dozens of FRBs have been detected by telescopes around the world. Each burst has unique characteristics, but they all share the common trait of being incredibly brief and energetic. The discovery of repeating FRBs, bursts that occur multiple times from the same location, added another layer of complexity to the mystery. Repeating FRBs, such as FRB 121102, allowed astronomers to pinpoint their locations with greater accuracy, often tracing them back to specific galaxies. In the case of FRB 121102, the source was identified as a small, star-forming galaxy about 3 billion light-years away. The precise origins of FRBs remain uncertain, but several theories have been proposed to explain their extraordinary nature. One leading hypothesis is that they are produced by magnetars, a type of neutron star, with an extremely powerful magnetic field. Magnetars are known to emit bursts of X-rays and gamma rays, and it's possible that they could also generate radio bursts under certain conditions. In fact, in 2020, astronomers detected an FRB-like signal from a magnetar within our own galaxy. providing strong evidence that at least some FRBs are linked to these exotic stars. Another possibility is that FRBs are associated with the merger of compact objects, such as neutron stars or black holes. These cataclysmic events release immense amounts of energy and could theoretically produce the kinds of radio waves observed in FRBs. However, this explanation doesn't account for repeating FRBs, as mergers are one-time events. This has led some researchers to suggest that there may be multiple types of FRBs, each with a different origin. Many FRBs have been traced to galaxies with high rates of star formation, suggesting a connection to young, massive stars or their remnants. However, others have been found in older, more quiescent galaxies, complicating the picture. The diversity of host galaxies implies that FRBs may arise from a variety of astrophysical processes, each influenced by local conditions. Because radio waves from FRBs travel through vast stretches of space, they are affected by the material they encounter along the way. This includes intergalactic gas, which can disperse and scatter the radio waves. By analyzing these effects, astronomers can learn about the density and composition of the universe on large scales. FRBs have already been used to measure the amount of ordinary matter, baryons, in the universe, helping to resolve a long-standing discrepancy between theoretical predictions and observations. The extreme brightness of FRBs also makes them useful for probing the properties of their local environments. For example, the polarization of radio waves from FRBs can reveal the strength and orientation of magnetic fields near the source. In the case of FAR-B 12-1102, highly polarized signals indicated the presence of a strong magnetic field, likely associated with a nearby black hole or a young supernova remnant. These findings provide valuable clues about the astrophysical conditions required to produce FRBs. Traditional radio telescopes, designed to observe steady sources, are not well suited for capturing such brief events. To address this challenge, astronomers have developed specialized instruments and algorithms capable of sifting through massive amounts of data in real time. Facilities like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, and the ASCAP have been particularly successful in discovering new FRBs, with CHIME alone detecting hundreds of bursts since it began operations. But many questions about FRBs remain unanswered. What triggers the bursts? Why do some repeat while others do not? Are all FRBs part of the same phenomenon, or do they represent a diverse group of events with different origins? Answering these questions will require not only more observations, but also theoretical models that can explain the full range of FRB properties. Because they occur over such vast distances, FRBs offer a unique opportunity to test fundamental theories about the universe. They can be used to study the behavior of light and matter under extreme conditions, such as strong gravitational fields or highly magnetized environments. Some researchers have even suggested that FRBs could be signals from advanced extraterrestrial civilizations, although this idea largely lacks supporting evidence. The enigmatic diffuse interstellar bands, cosmic chemistry unsolved. Diffuse interstellar bands, often referred to as DIBs, are faint absorption lines that appear in the spectra of starlight as it passes through the interstellar medium, the vast expanse of gas, dust, and particles that fills the space between stars. First discovered nearly a century ago, DIBs have continued to baffle astronomers and chemists alike. Their origin remains unknown, making them a tantalizing enigma in the quest to understand the chemical and physical processes at work in the cosmos. The discovery of DIBs dates back to the 1920s, when astronomers first noticed unusual dark bands in the spectra of certain stars. Unlike the sharp, well-defined absorption lines caused by known elements like hydrogen or helium, these bands were broad and diffuse, lacking the clarity that would link them to any specific atom or molecule. Over the years, researchers catalogued hundreds of these bands, each with its own unique wavelength, yet no definitive explanation for their origin emerged. One of the most intriguing aspects of DIBs is their sheer abundance. They are found in nearly every direction where interstellar material lies between a star and the observer. This ubiquity suggests that the carriers of DIBs, whatever they may be, are widespread and resilient, capable of surviving the harsh conditions of space. The interstellar medium is far from hospitable, bombarded by ultraviolet radiation, cosmic rays, and extreme temperatures. Any molecule or particle responsible for DIBs must be robust enough to endure these challenges. The leading hypothesis is that DIBs are caused by complex organic molecules, possibly polycyclic aromatic hydrocarbons or PAHs or fullerenes, which are carbon-based structures known for their stability. PAHs are flat, ring-shaped molecules that form naturally in a variety of environments, from combustion processes on Earth to the outer regions of dying stars. Fullerenes, such as the famous buckyballs, are spherical molecules made entirely of carbon atoms. Both types of molecules are thought to be abundant in space, and their absorption properties align with some of the characteristics of DIBs. Despite these promising leads, no single molecule or group of molecules has been conclusively identified as the source of DIBs. The problem lies in the complexity of the interstellar medium. Unlike laboratory conditions, where variables can be tightly controlled, the interstellar medium presents a chaotic mix of factors that influence how light interacts with matter. Temperature, pressure, radiation, and the presence of other molecules all play a role in shaping the absorption spectra. Reproducing these conditions in a lab is challenging, making it difficult to match the observed DIBs with known substances. Adding to the mystery is the variability of DIBs. Some bands appear stronger or weaker depending on the direction of observation and the density of interstellar material along the line of sight. This variability suggests that the carriers of DIBs may interact with their environment in complex ways, possibly changing their structure or alignment in response to external forces. Understanding these interactions is key to unraveling the puzzle, but it requires detailed observations and sophisticated modeling. At their core, DIBs are a window into the chemistry of the interstellar medium, offering clues about the processes that govern the formation and evolution of matter in space. The interstellar medium is not just an empty void. It is a dynamic environment where atoms and molecules combine, break apart, and recombine, setting the stage for the birth of new stars and planets. By identifying the carriers of DIBs, scientists can gain insights into the building blocks of cosmic chemistry and the conditions that give rise to complex organic compounds. Many of the molecules proposed as DIB carriers are precursors to more complex organic structures, including amino acids and other biomolecules. If these compounds are widespread in the interstellar medium, they could be delivered to young planets via comets, asteroids, or interstellar dust, seeding the raw materials for life, an idea known as panspermia. High-resolution spectroscopy allows astronomers to analyze the absorption lines in detail, revealing subtle features that might hint at their origin. Infrared and ultraviolet observations can probe regions of the spectrum where many organic molecules exhibit characteristic absorption patterns. Advances in telescope technology, such as the deployment of space-based observatories like the James Webb Space Telescope, are opening new windows into the study of DIBs, enabling researchers to observe them in unprecedented detail. One promising approach is the use of laboratory experiments to simulate the conditions of the interstellar medium. By subjecting candidate molecules to intense radiation, low temperatures, and other space-like conditions, scientists can measure their absorption spectra and compare them to the observed DIBs. These experiments have already ruled out some potential carriers and narrowed the field of possibilities, but much work remains to be done. Another avenue of research involves studying DIBs in different environments, such as dense molecular clouds, diffuse regions, and the outskirts of galaxies. Comparing the properties of DIBs across these settings can provide clues about how the carriers form and evolve. For example, some DIBs are stronger in regions with high ultraviolet radiation, suggesting that the carriers may be linked to photochemical processes. Others appear more prominently in dense clouds, pointing to a possible connection with dust grains or icy mantles. The study of DIBs also intersects with other fields of astronomy, such as the search for exoplanets and the study of stellar atmospheres. As light from distant stars passes through the interstellar medium, it carries the imprint of DIBs, along with information about the stars themselves. By carefully analyzing this light, astronomers can disentangle the contributions of the interstellar medium and the star, gaining insights into both. The South Pole Wall, a hidden structure in our galactic backyard. The South Pole Wall is one of the most recent discoveries in the ever-expanding map of our cosmic neighborhood. Located relatively close to the Milky Way, this massive structure spans 1.37 billion light-years and represents one of the largest known continuous features of the universe. Despite its enormity, it had remained hidden from view until recently, shielded by the dense regions of stars, gas, and dust in our own galaxy. As we know, galaxies tend to cluster together, forming structures that resemble a vast cosmic web. The South Pole Wall is one of these structures, a massive wall of galaxies and matter stretching across roughly 1.4 billion light-years of space. It is comparable in size to other well-known structures like the Sloan Great Wall and the Hercules Corona Borealis Great Wall, though it stands out because of its relative proximity to Earth. It lies in the zone of avoidance, however. Advancements in technology and new methods of mapping the sky have allowed researchers to peer through this veil. By analyzing the motion of galaxies and using data from surveys that detect light outside the visible spectrum, scientists were able to uncover the existence of this massive wall. The discovery of the South Pole Wall was announced in 2020 by a team of astronomers using data from the Cosmic Flows 3 survey. This survey focuses on measuring the motions of galaxies, particularly their peculiar velocities, movements that deviate from the general expansion of the universe. By mapping these motions, the team could infer the distribution of mass, revealing the gravitational influence of the South Pole Wall even in areas where it could not be directly observed. This method of studying the universe, often called cosmic cartography, has become an essential tool for understanding the hidden structure of the cosmos. The proximity of the South Pole Wall to the Milky Way adds to its significance. At a distance of around 500 million light-years, it is relatively close in cosmic terms, making it one of the nearest large-scale structures to our galaxy. Its discovery raises questions about how such a massive feature could have gone unnoticed for so long. The answer lies partly in its location behind the zone of avoidance and partly in the limitations of previous surveys, which lacked the sensitivity and coverage to detect it. The South Pole Wall is not a single continuous structure, but rather a complex arrangement of galaxies, galaxy clusters, and filaments, interconnected in a vast, elongated formation. It stretches across the southern celestial hemisphere, earning its name from its alignment with the south celestial pole. The structure's density and composition make it a key feature of the local cosmic web, influencing the motions of galaxies in its vicinity and shaping the distribution of matter on a regional scale. Massive structures like this exert a significant gravitational influence, pulling nearby galaxies and galaxy clusters toward them. This movement contributes to the peculiar velocities observed in galaxy motions, which are deviations from the smooth expansion of the universe described by Hubble's law. The South Pole Wall is also a reminder of how much we have yet to learn about the cosmos. Despite decades of advancements in astronomy, large portions of the sky remain unexplored or poorly understood, particularly in regions obscured by the Milky Way. The discovery of this massive structure highlights the importance of continuing to develop new technologies and methods for observing the universe. It underscores the need for comprehensive sky surveys that can map the distribution of galaxies and matter across all regions of the sky, including the challenging zone of avoidance. Polar ring galaxies, galactic rings defying gravity. Polar ring galaxies are rare galaxies featuring a main body, often resembling a standard elliptical or lenticular galaxy, encircled by a ring of stars, gas, and dust that orbits at a steep angle, nearly perpendicular to the galaxy's plane. The result is a cosmic formation that appears to defy the usual rules of gravity and galactic dynamics. The defining feature of a polar ring galaxy is its ring, which orbits around the main body at a right angle. This configuration is highly unusual in the universe, where most galactic structures tend to align along a single plane. The ring itself is composed of stars, gas, and dust, and it can vary greatly in size and brightness. Some polar rings are faint and subtle, while others are bright and expansive, extending far beyond the main galaxy's visible boundaries. The material in the ring orbits in a stable, coherent manner, indicating that it is held together by the gravitational pull of the galaxy's central mass. The formation of polar ring galaxies is thought to result from galactic interactions and mergers. One leading theory suggests that these structures form when a smaller galaxy passes close to or collides with a larger galaxy, stripping away material that is then captured by the larger galaxy's gravitational field. This material, consisting of gas, dust, and stars, settles into an orbit around the main galaxy, eventually forming the distinctive ring. The orientation of the ring is determined by the dynamics of the collision and the angles at which the galaxies interact. Another possibility is that polar rings form through the accretion of material from intergalactic space. In this scenario, a galaxy might capture gas and dust from a nearby filament of the cosmic web, the vast network of matter that permeates the universe. This material, drawn in from a direction perpendicular to the galaxy's plane, could form a ring-like structure over time. While this process is less common than galactic collisions, it provides an alternative explanation for the existence of polar ring galaxies. Polar ring galaxies are exceedingly rare, making them valuable subjects for study. Their scarcity suggests that the specific conditions required for their formation are uncommon. For example, the relative velocities and angles of interacting galaxies must align in just the right way to produce a polar ring. Additionally, the captured material must have enough angular momentum to settle into a stable orbit rather than being absorbed into the main galaxy. These constraints help explain why only a few dozen confirmed polar ring galaxies have been observed. One of the most famous examples of a polar ring galaxy is NGC 4650A, located approximately 130 million light-years away in the constellation Centaurus. This galaxy features a bright central core surrounded by a striking ring of stars and gas. Observations of NGC 4650A have revealed that the ring contains a significant amount of neutral hydrogen gas, a key ingredient for star formation. This suggests that polar rings are not merely static structures, but dynamic environments where new stars can form over time. The study of polar ring galaxies provides valuable insights into the nature of galactic interactions and the dynamics of rotating systems. By analyzing the motion of stars and gas in these galaxies, astronomers can learn about the distribution of mass within the galaxy, including dark matter. Polar rings are particularly useful for this purpose because their perpendicular orientation allows scientists to measure the gravitational effects of the galaxy's dark matter halo from different angles. This unique perspective can help refine models of dark matter distribution and improve our understanding of how galaxies are structured. The rings must be in a delicate balance to maintain their orbits without collapsing into the main galaxy or dispersing into space. This stability is achieved through a combination of gravitational forces and the angular momentum of the ring's material. The precise conditions that allow these structures to persist for billions of years are still an active area of research, with scientists using both observations and computer simulations to explore the dynamics of polar rings. The appearance of polar ring galaxies can vary widely, depending on the angle from which they are viewed. When seen edge-on, the ring can appear as a faint line cutting across the main galaxy, while a face-on view reveals the full circular structure. This variability adds to the challenge of identifying polar ring galaxies in the vastness of the universe. By studying these galaxies, astronomers can gain insights into the processes that shape galaxies over time, from mergers and collisions to the influence of dark matter and intergalactic gas. They serve as natural laboratories for exploring these phenomena, offering a glimpse into the dynamic and interconnected nature of the universe. Despite their rarity, polar ring galaxies are not isolated anomalies. They are part of the broader spectrum of galaxy types and structures that populate the cosmos. Each polar ring galaxy is a unique snapshot of the universe's history, capturing the aftermath of interactions and the interplay of forces that govern the motion of stars and gas. Hoag's Object, the perfectly circular galaxy mystery. Discovered in 1950 by astronomer Arthur Hoag, Hoag's object stands out due to its nearly perfect circular ring of stars encircling a dense spheroidal core. This configuration makes it unlike most other galaxies, where the structures typically form spirals, ellipses, or irregular shapes. Hoag's object immediately drew the attention of astronomers, not only for its aesthetic appeal, but also for the mystery of how such a symmetrical structure could come into existence. The galaxy lies approximately 600 million light-years away in the constellation Serpens. Its most defining feature is the luminous ring, composed of young blue stars that shine brightly against the darker backdrop of space. These stars suggest ongoing star formation within the ring, indicating that it is an active region rather than a static one. At the center of the ring is a reddish-yellow core, which appears to consist of older, cooler stars, typical of a galactic bulge. What makes Hoag's object so intriguing is the vast, empty gap of space separating the ring from the core, a feature not commonly observed in other galaxies. One of the earliest challenges in studying Hoag's object was determining its classification. It does not fit neatly into the standard categories of galaxies, spiral, elliptical, or irregular, leading some astronomers to consider it a rare type of ring galaxy. However, even among ring galaxies, Hoag's object is unusual due to the almost perfect circularity of its ring and the isolation of its core. Most ring galaxies display some irregularities or have connections, such as spiral arms or bridges of material, linking their rings to the central structure. In contrast, Hoag's object seems to lack these features, adding to the enigma of its origin. One prominent hypothesis is that it formed as the result of a galactic collision or interaction. According to this theory, a smaller galaxy may have passed through the center of a larger one, disturbing the distribution of gas and stars. The gravitational forces involved in such an interaction could have pulled material outward, creating a ring while leaving the central core relatively undisturbed. Over time, the material in the ring would coalesce into new stars, giving rise to the bright, star-forming region observed today. Another theory suggests that Hoag's object might have formed through a process known as resonance. In this scenario, gravitational interactions within the galaxy itself, perhaps involving a central bar or a massive dark matter halo, could have created a wave-like motion in the gas. This motion might have caused the gas to accumulate in a ring-like structure, where it would eventually condense into stars. This explanation does not require an external galaxy to be involved, making it a more self-contained model. However, the lack of visible structures like a bar or spiral arms in Hoag's object complicates this theory. Some astronomers have proposed that Hoag's object might represent a rare stage in the evolutionary history of a galaxy. It is possible that it was once a spiral galaxy whose outer arms were stripped away by tidal forces during an encounter with another galaxy. The remaining material could have settled into a ring, while the core retained its spheroidal shape. This idea aligns with observations of other ring galaxies, which sometimes show remnants of spiral structures or evidence of past interactions. However, Hoag's object appears remarkably clean and symmetrical, with no obvious signs of such disruptions. In the background of the galaxy, visible through the ring, is another ring galaxy, much smaller and fainter. The alignment of this background galaxy is purely coincidental, but it has fueled speculation about whether similar processes might be responsible for the formation of both objects. While there is no evidence to suggest a direct connection, the presence of the background galaxy serves to intrigue the mind. Hoag's object has been the subject of numerous observational studies which have provided detailed images of the galaxy, revealing the fine structure of the ring and the properties of the stars within it. Spectroscopic analyses have also been conducted to measure the motion of stars and gas in the galaxy, offering clues about its dynamics and mass distribution. Despite these efforts, many questions about Hoag's object remain unanswered, highlighting the limitations of current technology and our understanding of galactic physics. In the case of Hoag's object, the dark matter halo surrounding the galaxy might have contributed to the creation and maintenance of the ring by providing additional gravitational support. Understanding how dark matter influences such unique structures could provide valuable insights into its properties and behavior. While most galaxies can be classified into well-defined categories, objects like Hoag's demonstrate that the cosmos is far more varied and complex than these categories suggest. The study of such outliers helps refine our models of galaxy formation and evolution, ensuring that they account for the full range of possibilities observed in nature. Phantom galaxies, the peculiar case of ultra-diffuse systems. At first glance, ultra-diffuse galaxies might seem like empty patches of sky, but careful observations reveal their faint outlines. These ghostly galaxies challenge many of the assumptions astronomers have held about what a galaxy should look like. They are large, often comparable in size to the Milky Way, yet they contain far fewer stars. This combination makes them appear almost invisible against the darkness of space, earning them the nickname phantom or dark galaxies. Unlike the dense and compact galaxies we often picture, these systems are incredibly sparse. Their stars are spread out over a vast area, creating a dim glow that is difficult to detect. Some of the most well-known examples of these galaxies were first discovered in the Coma Cluster, a region teeming with thousands of galaxies. Among the bright, bustling members of this cluster, the ultra-diffuse galaxies stand out for their quiet, understated presence. Their large size suggests they should contain significant amounts of mass, yet their low luminosity indicates a lack of stars. This contradiction has led scientists to explore the role of dark matter in their formation. Without it, their sparse distribution of stars would likely drift apart. But a few examples, such as DF2 and DF4, have been observed with very low dark matter content, challenging the idea that dark matter is essential for galaxy formation. These galaxies appear to consist almost entirely of stars, gas, and other visible matter. Their existence raises new questions about the processes that create and shape galaxies. Did they lose their dark matter through interactions with other galaxies, or did they form in a way that bypassed the need for dark matter altogether? Many of these galaxies are dominated by older, redder stars, suggesting that their star formation peaked long ago and has since tapered off. This lack of ongoing star formation could be due to the galaxies losing their gas, either through interactions with their environment or through internal processes. Without gas, the raw material for creating new stars, these galaxies are left to fade over time. In some cases, ultra-diffuse galaxies have been found to contain surprisingly rich populations of globular clusters. These dense groups of stars orbit the galaxy's core and are often used as a proxy for measuring a galaxy's total mass. The presence of numerous globular clusters in an ultra-diffuse galaxy can indicate a massive halo of dark matter, even if the galaxy itself appears faint. Many of them reside in dense galaxy clusters, where interactions with other galaxies and the cluster's hot gas can strip away material and reshape their structure. This process, known as ram pressure stripping, occurs when a galaxy moves through the dense intra-cluster medium, losing its gas and becoming less able to form new stars. Over time, this can lead to the formation of an ultra-diffuse galaxy. However, some of these galaxies are found in isolation, far from the influence of larger clusters. These isolated examples suggest that multiple pathways may lead to the creation of ultra-diffuse galaxies. Traditional surveys often miss them because of their low surface brightness. However, specialized telescopes and instruments designed to detect faint objects have made it possible to identify and study them in greater detail. Deep imaging surveys using telescopes like the Subaru telescope Hubble have revealed hundreds of these elusive galaxies. The development of new technologies, such as wide-field detectors and sensitive spectrographs, continues to push the boundaries of what can be observed. Studying how these galaxies interact with their environment can reveal how galaxies lose their gas and how their structures are shaped by external forces. Similarly, investigating the relationship between their dark matter content and their visible components can shed light on the nature of dark matter itself. With their faint appearance, ultra-diffuse galaxies are a reminder that the universe is full of surprises, with hidden structures waiting to be uncovered. As technology advances and more data becomes available, the study of these phantom galaxies will likely continue to yield new insights, deepening our understanding of the cosmos and its many mysteries. Though this ride has come to an end, were there any crazy cosmic structures that you'd like for us to cover next? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.